but that says S. It looks like not V. So that should be a volumetric. Let me just see what he does here. Tell you what, I'll take you through this, but I'm going to do it. I'm going to do it using the doc cam and show you. No, I thought I would show you. How many do we have now? How many people? We're missing some. Okay. Y'all can see this equation, right? This is really called Poisson's equation. I think you're familiar with this. And this comes from, you create this equation by saying E is equal to minus the gradient of V, and then you know divergence of E is equal to rho V over epsilon. So when you place minus gradient of V in here for E, you get the divergence of minus the gradient of V equal rho V over epsilon. And then you multiply both sides by a minus sign. And the divergence of the gradient operator is in fact the del squared. It's the Laplacian, del squared over epsilon. That's how that comes about. Now, that was from the last lecture. Now, when you want to apply this, if you want to use this equation, this is the differential equation that describes the behavior in any region. You have to first find out, well, what coordinate system are you in? And it's obvious you're in cylindrical coordinates. So for cylindrical coordinates, when you look in the book, there are three terms to the derivative. The first is equal to, when I do del squared, this is equal to 1 over rho, and then it's going to be d rho of rho times dv d rho. That's the first term. You'll notice it's a scalar. Then there's a second term, the second derivative of v with respect to z squared. And then there's a third term. And in his book, I don't know if he has, or he does have it at the back. If you're wondering where I'm getting this, if you look in the back of the book on page, the very back of your book cover, and you look in cylindrical coordinates, I'm using this right here. It's the middle one. And then you have plus 1 over r squared, or 1 over rho squared times the second derivative of v with respect to phi squared. Now, can everybody follow me up to this point? I'm just setting up the differential equation, right? John, can you guys see this? Everybody see this okay? I'm just trying to make sure you all understand. This is the equation that would replace the del squared v operation. Now, here's the thing. In cylindrical coordinates, if it's cylindrically symmetric, the voltage is not going to change versus phi, all other things being held constant. So dv d phi would be 0. Do you all follow me on that? Guys? All right. Also dv dz, it's supposedly infinitely long, so it will not have a change in voltage with respect to the height, if you will, this value z. So that goes to 0. This is the only thing you worry about. That's the differential equation. So you have 1 over rho, or the derivative with respect to rho of rho dv d rho, and that's equal to the charge minus the charge density over rho v. Now, let me just see, in his problem statement, he says that this is a charge density in the dielectric, but that says surface. Let me see what he actually does. Oh, he puts it in here. He actually says that's a volumetric charge density. So now I have to say this. The volumetric charge density is some constant, call it rho 0 over rho. And that would be in coulombs per meter cubed. Tyler, I hope you can see this, right? So now I put that over here. That's minus, right? What rho v is, which is minus rho 0 over rho divided by epsilon. And I'm going to call that epsilon naught. I don't, I guess you don't have to, but I'm going to just leave it as epsilon naught. Everybody with me? How many people do we have here? No, I can't tell.
Still 5.
Just 5 people? So we're missing Carolyn. Who else we missing? Oh, we're missing a bunch. Hopefully they'll tune in eventually. Okay, now, y'all see at this point what I'm going to start doing. Now follow me. I'm here, and you understand how I got there, right? Now I'm going to multiply both sides by rho, thereby getting rid of it. Y'all see this? Now I multiply both sides by d rho, and I have this. Y'all follow me? Oh, I'm sorry. It's blurry. Come on. All right. I'm multiplying both sides by rho, so it gets through this term, and then d rho. So d rho comes here, d rho comes out here. Now I have a perfect differential. I have the differential of whatever that is. When I integrate it, now I integrate both sides. When I integrate this side, I simply get rho dv d rho. On this side, I'm going to get minus rho naught over epsilon naught rho plus a constant C1. Do y'all agree with that? Everybody see what I did here? I'm just following through the mathematics, right? To get V as a function of rho. So I have rho naught, whatever that is, over epsilon, it's just from here, plus some C1. Now, the next step's fairly obvious. I divide both sides by rho, correct, class? So when I divide by rho, it gets rid of this one, and it puts a rho down here. So in my doings, now I get this. I have dv d rho is equal to just minus rho naught over epsilon naught plus C1 over rho. And now to get the final form of V, I'm going to multiply both sides by d rho. That goes away. Everybody agree with that? And now I have to integrate, right? So if I integrate both sides, I get V as a function of rho is equal to, well, this one becomes minus rho naught over epsilon naught, right? Times rho. And then this one is going to be plus C1 times the natural log of rho plus C2. Y'all agree with that? Now you apply boundary conditions, and there's 2 boundary conditions. I think one is the inner value is V naught and the outer value is 0, right? Or he uses an alpha in here, but I'm just going to call it V naught at rho equals. Does he use A? I don't know what he uses.
I think he uses VA.
Well, no, okay. You can use VA, but A is the inner radius, right?
Right.
Okay. So now this is fairly straightforward if you think about it. Now I say that V rho equals A is just VA, and that's equal to minus rho naught over epsilon naught A, right? Plus C1 times the natural log of A plus C2. I'm just plugging in values, correct, class? Go ahead, catch up with me. Okay. Now, the outer, at radius B, it's Z. So then you say that V at rho equal B is equal to 0, right? And that's equal to, use this equation, minus rho naught B over epsilon naught plus C1 times the natural log of B plus C2. Y'all agree with me there? And at this point, you can do it any way you want, but what you can obviously see is we have 2 equations and 2 unknown constants, right? So if you're going to solve for this, normally what you do is solve for one constant in terms of the knowns and then plug it into the other one. I don't know how you prefer to do this, but if you go ahead and you just subtract the lower equation from the upper equation here, we would get VA, right, equal to, and then subtracting these two, I'm subtracting this one from this one, you would have rho naught over epsilon naught, and then it would be B minus A. And then subtracting these, you're going to get plus C1 times the natural log of A over B, right? And C2 goes away. Do you agree with that? And here, you know that if this is BA here, you can solve for C1, can't you? Y'all see this? You can say that now, take this to the other side and then divide by C1 and take everything to the exponential power. And I think he does. I'm just seeing what. He basically does that, but I got to flip the page on this one. So now, when I have this equation right here, if I'm solving for C1, sorry, if I have this equation and I'm solving for C1, I'd go ahead and I'd have VA, right? And then it would be, if I take this to the other side, then it's going to be plus rho naught times A minus B over epsilon naught, right? Would be equal to C1 times natural log of A over B. So I'd take this whole thing and divide by the log of A over B, and therefore I'd have C1, right? And now you can take this C1 and plug it into this equation and get C2. And then plug it into here. So if we plug this equation into this equation, we have 0 is equal to minus rho naught over epsilon naught plus, and then this is C1 here, so it would be VA plus rho naught over epsilon naught times A minus B over the natural log of A over B times the log of B plus C2, and C2 is, yeah, just plus C2. So I can solve for C2 right here, and I find out that C2, just take it to the other side. So make this minus C2 here, and then multiply everything by a negative sign. And that would be C2. Do y'all agree with this, class?
Professor, on the rho naught over epsilon naught, should that have a B, like in that term? Is that right?
I'm going right here. Yeah, you're right. You're absolutely right.
Okay.
That's my bad. That's my bad. It's right here. Yeah. And now you have C2 and you have C1 right there. So you just pop those back in the equation, and there's going to be some cancellation. So when I get the original equation here, I find that V of rho, it's kind of a long one, but there's going to be a lot of cancellation, is equal to minus rho naught times rho over epsilon naught plus C1, and C1 is up there, plus VA plus rho naught times A minus B over epsilon naught, all over the natural log of A over B. That's C1 times the natural log of rho plus C2, and C2 would be this, which, so it's, now you have rho naught B over epsilon naught times VA plus rho naught over epsilon naught times a minus b all over the natural log of a over b. And that's it. Now, I'm going to just tell you this. You can simplify this a lot if you want, but you see the variation with rho is here and here. Right there, that's a rho. Everything else are constants. You give me exact values for A, B, VA, then I can give you the exact value for the constants, and you'd need rho zero. But that's the form it takes. And in Wentworth's book, he has this as the final answer. Right there. And let me tell you a couple of tricks. When I'm looking at this log of A over B, all right, I see he has that. If you look right here, let me see if I can move this out. If you look right here, this is the coefficient of the natural log, right? And if you look, here's the log of A over B. That's it. VA, oh gosh. VA plus rho naught A plus B. I'm sorry. I think I should have put a minus there, my bad. That's supposed to be a minus right there. A minus B. And then here's log rho by itself. But he has to divide by B. So let's see. If I flip this right here, you know, if I have natural log of A over B, that's really equal to the log of A minus the log of B, right? Right. And if you take a look at this, 1 over the log of A over B, that's equal to minus the log of B over A. And I think this is going to be just manipulation. Let me just see here. Oh, did he want the E field? Is that what he really wanted in this problem?
He wanted the voltage and the E field, and then the surface charge density.
All right.
Both of the surfaces.
I'll tell you, for the E field, when you look at the final form of the equation, which is, this is the form of the equation right here, the final form. The E field is going to be minus the gradient of the voltage. So you would take a derivative with respect to rho, and you would get, and I'll do this, it would be minus the derivative of this. So I know it's a little messy, but can you all see this is really supposed to be the log of rho there. If you take a derivative of this with respect to rho to get the E field, which would be minus dV d rho, the first term, I take a derivative just as, is going to be just rho naught over epsilon, but it'll be positive because it's got a negative sign in front of it. Then the second term, when I take a derivative of the natural log, right, I get 1 over rho again, don't I, class? So I would get just this constant divided by rho, so, and it would be with a minus. And I have a 1 over rho here. And this term would go away because it's just a constant when I take a derivative. So that would be the E field. Let's see what he has for the E field. He actually has a plus or a minus rho naught over epsilon. Well, let's just see for a second. If this is his V, wait a second. There's rho, right? Just follow me on this. Can you see where my cursor is, class? Everybody? You see the cursor right here next to rho? This is his equation for V. Think about this logically. If we, let me kill my email, hold on. If we take a derivative of this with respect to rho, we're going to get simply rho naught over epsilon, correct? Now, that's V, dV d rho, but when we throw a minus sign in, it would be minus rho naught over epsilon. So the E field here yeah, he has minus rho naught over epsilon.
I think he may have made a sign error at the beginning of the problem because I did the problem and I got very similar results, but I think he made a sign error like in one of the first steps. Where like that very first step, it should be minus rho v over epsilon, but then the next part, it shouldn't be minus 1 over rho d d rho. It should just be 1 over rho d d rho, rho dv over d rho, right?
Are you talking about what
Right in the very first step.
all right, right here, up here?
Yes, that very first line, it should be minus rho v over epsilon, but the next part shouldn't have a minus sign in front of it because that gradient squared v doesn't have a minus sign in front of the.
Well, what he does, he's trying to translate this equation right into here, okay?
Right.
And when he does it, he has 1 over rho times dv d rho is equal to, and this should be rho 0 over rho epsilon with a minus sign right there in
Right.
front. And you're right, he doesn't do that. Now, right here, you can get the E field if you look at this. If you put a minus sign right there in front of that rho 0, if you just divide by rho, well, first of all, just leave it like he has it. First, if you divide by rho, then you have rho naught over epsilon plus A over rho, correct? You see what I'm talking about? There's a rho we got to get rid of first right there. So divide this side and that side by rho. You get dV d rho is equal to rho 0 over epsilon plus A over rho. Do you all see that? Now, once you throw a negative sign in front of that, then you would have the value of the E field. Minus dV d rho is the E field. And in case you're wondering what the gradient operator is in different coordinate systems, let me move that out of here for a second. Well, if you look here, the gradient operator in cylindrical is just dV d rho, A rho, plus 1 over rho dV d phi, which is 0, plus dV dz, which is 0 az. But this one, you'd have to put a negative sign to get the E field. Do y'all follow me on this? Honestly, this is just a problem with a lot of constants that you have to organize and keep track of. It's not conceptually very hard. Y'all agree with that? I'll just tell you this. Generally speaking, when you're doing these problems, if you're doing any type of problem that has to do with a differential equation and solving for any kind of a, either the E field, D field, to get the, by the way, the charge density on the surface, let me take you through this in general. If you have the equation del squared of V, del squared of V is equal to minus rho V over epsilon as a starting point. You come down to the coordinate system you're in. It could be spherical, it could be cylindrical. And then you'll break this thing out into its differential equation. Now, in cylindrical, if it's cylindrically symmetric, you get 1 over rho d rho of rho times dV d rho. That's what del squared would be. And it would be minus rho v whatever rho v is, could be a function of position over epsilon. That's the next step. Then you multiply by rho. Now you have this. Then you multiply both sides by d rho, get rid of that. Then integrate both sides. So you would have minus the integral of rho v, rho over epsilon, d rho is equal to simply rho dv d rho. Now remember, I didn't put any limits on here. So when I do this first integration right here, I have to add a constant. With me? When you do this, when I go ahead and I'm going to integrate this thing, whatever the results are, I'll have to add a constant to it. You understand why? Because it's indefinite. There's no limits. If there were limits, I wouldn't have to add that constant. Then you have to divide by rho. Now I have that. And finally, you have to take and multiply again by d rho. And then integrate again. And integrating this will give me a second constant. So I'd have v as a function of rho would be equal to the integral of minus 1 over rho, the integral of rho v, rho over epsilon d rho, right? That's the first one. And then right in here, I also have to put plus c1 over rho. And then I get my second integration, and finally C2. That's the way it's going to be. And here, rho v is any function. It could be a function of rho. That's what you have to do. He spends a lot of time just organizing constants, and I think you're right. I think right here looks like that's correct, the top line. Here is where, right here, he doesn't put the negative in front, right in here. Y'all see that? Now, Tyler, once we get the E field, let's just assume we get the correct value for the E field by taking either a gradient of the final form of the voltage, say this form of the E field is correct. Then to get the surface charge density, you get the D field, and just multiply this by epsilon. That would be D, correct, class? Epsilon E is D. And evaluate it at the surface, because this is normal to the surface. So if you evaluate the D field on the surface of the interconductor, you have the charge density. And that's what he should do. Yeah, D normal is rho s, or the charge density on the surface. So he does that to evaluate. But I think you're absolutely right that there's a sign error right there. All right. I hope I answered your question.
Yes, you did. Thank you.
Any other questions about this capacitor problems? This one, this is that bad problem. It's pretty good actually, but he uses a sine function. And any questions about these? Because this I didn't give.
Would you mind posting the answers on those if you get a chance?
Yeah, I think we can. Problems. Didn't I post these answers 362, 363, 371?
Yeah, we got those, but like the problems that you
this
wrote.
One?
Yeah.
All right, let's go through it first of all. A material has this is the voltage, right, inside a dielectric, and the breakdown electric field is 15 megavolts per meter. Will this voltage be exceeded and the dielectric break down? And if it does, where does it break down? So how do you figure out if that voltage is exceeded? First, the breakdown strength is 15, right? Let me go ahead and do this one, because that's a good problem. So first, I'm going to say that I have an equation, x cubed plus, I have this equation, a v of x is equal to x cubed minus 6x squared minus 3x times 10 to the 6th, and that's volts, right? This is problem 3 that I've assigned. to get the volt, or to get the electric field, I know that E is equal to minus the gradient of V, right? We're in Cartesian coordinates, so that means it's minus the V of X dx. Does everybody agree with that? Y'all hear me okay on this one? Right. So I've got to get this derivative. Well, and if I take a look at this derivative, E would be equal to, when I take a derivative of this, the first one is going to be just 3x squared, all right? The second one is going to be minus 12x, and the third one is minus 3 times 10 to the 6th, and that would be volts per meter. And I can put a minus sign out in front of it if I want to get the total E field. Do you all agree with that? And that would be in the AX direction. The direction is not a consequence in this problem. Are you good at this, everyone? Now, what do you want to do? You want to see where this is a maximum, don't you? They want to see if the maximum value of the E field is greater than 15 megavolts, right? Anybody, how do you get a maximum? How do you figure out where the maximum is, first of all? Anyone? Go ahead, Haran. Were you about to say something? Ben?
You can set that derivative equal to 0 and solve for x.
We're going to have to take another derivative, right?
Okay.
This is the E field. We have to find out where the E field's a maximum, so we first take another derivative. So we get dE dx, right? And that means I have minus, and then inside here, now I have 6x, right? And then here I have minus 12 times 10 to the 6th. And we're setting that equal to 0, correct? Now, the 10 to the 6 you can get rid of. That's a scale factor. So, and I can get rid of the minus sign, but I can say that 6x is equal to 12, and that means x is equal to 12 over 6, or 2. So that's where the maximum magnitude takes place, right, class? Everybody follow me? That's the relative maximum. So then you go back to the E field equation and evaluate what the voltage is. And the E field at x equals 6, or at 2, pardon me, x equals 2 is minus, and it's going to be 3 times 2 squared minus 12 times 2 minus 3 times 10 to the 6th. And that equals what? It's minus the quantity, that's 4 times 3 is 12, minus 2 times 12 minus 3 times 10 to the 6th. And therefore, you can see what this is going to be. 12 minus 2 times 12 is just minus 12. Minus 3 is minus 15, right? Or really 15 times 10 to the 6th volts per meter. And that's right on the button. It's 15 megavolts. You agree with that, class? So if in fact 15 megavolts is reached and it breaks down, it will break down right at 2 meters. That's the moral of the story. Do you agree with that? Okay. What about this part? A spherical capacitor. You know, this is my own belief that the more problems you can work in front of people, especially that they have questions about, if you can come to class and you're ready, you've got formed questions about things you don't understand, when you answer them is the best way to show how these theories and equations apply to real problems. You can spend all day giving PowerPoints of showing just general theories, but when it's applied is where it becomes real to you. All right, so a spherical capacitor, inner radius A, outer radius B, has a charge Q on the inner plates and permittivity 1.2 R. Determine the values of the electric field and the voltage developed. The only thing you really care about is the epsilon relative is 1.2 R. So let me go ahead and do this. The D field's natural, it comes. All right, so we have a spherical capacitor or spherical system with inner radius A, outer radius B, and in here I have epsilon relative is equal to 1.2 R. You all with me, everyone? All right, how do I go about, if I ask for the capacitance between these two plates? This is a good question. With capacitor problems, you assume Q, right? Anything but planar, you assume Q. Do you agree with me? Now, after that, I get D. It's Q over 4 pi R squared AR because of spherical symmetry, correct, class? How many people do we have here now? I can only see a couple hands.
6.
6 people? All right, are you with me so far? Now, once I have D, I need E, so what do? I'm going after voltage. Anyone? It's D over epsilon, right? And now I have to put in the value of epsilon relative and epsilon naught. So I get Q over 4 pi, and then it's going to be times 1.2 here, times R cubed AR. Agreed? Then what do? Anyone? What am I after? The voltage, right? So now I have to integrate this, and I'm going to integrate it and evaluate it between the inner and outer conductor. So when I get VBA, it would be equal to the integral of Q over 4 pi times 1.2 R cubed AR dot AR dr, because that's DL. And I'm going to go from A to B, or B to A, pardon me, B to A with a minus sign. And when I do that, now I get Q over, and there's an epsilon naught I forgot there. Should be an epsilon naught there. The AR's dot away. And now I have 4 pi, right, times 1.2. The integral of 1 over R cubed is really the integral of R to the minus 3, right? So I'm going to have 1 minus 3 downstairs, and then I'm going to have R to the minus 3 plus 1, or R squared. And here it's evaluated from, really that's going to be a negative, so from A to B, and it reverses them, so I end up getting what? Q, my voltage between B and A would be equal to Q over 4 pi 1.2, and then it's minus 2, right? Or make it plus 2 and just switch the limits. Then it's going to be 1 over A minus 1 over B, or 1 over A squared minus 1 over B squared. Do y'all agree with me there? Right, because if you have 1 over R cubed and you integrate it, you get 1 over R squared, and you have a factor of minus a half in front of it. Are you with me, class? When you do the integration, you're going to get a minus 1/2 in front of there. And when you just modify this, this voltage will always be positive. You have 1 over R squared evaluated between A and B, but because this is going to be minus 2, I can flip the boundaries and make the A first, and I have 1 over A squared minus 1 over B squared. That's the voltage, correct, class? How many see that as the voltage, just so I can be sure? Tyler? Got it? All right, now the final thing is I need the capacitance, so what do? Let me try to turn that intensity up on this line.
Divide charge by that voltage.
That's right. To get the capacitance, it's going to be equal to Q over V, and it really just erases this Q right here. It takes 1 over everything. So if I take 1 over everything, sorry, it's blurry, it's 4 pi. This comes up top, so I have 4 pi times 2 times 1.2, and then it'll be over 1 over A squared minus 1 over B squared. There. And I'll tell you one of the problems I'll see. People do this all the time. What I'll end up saying is when you take 1 over this, you get a squared minus b squared. They'll find some way to make it and make an error just taking 1 over this term. Think of that as a constant c. So 1 over that is 1 over c, just replace c with that. Okay, that's that problem. This is Friday. And okay, for the last one, or for this one, it says it's assumed you have a 1 meter length and epsilon relative is 2 rho. What's the value of the capacitance? How do you do that one? This is problem 5. Anyone? Epsilon relative is 2 rho. So how would you do it? If you have a cylindrical capacitor, inner radius A, outer radius B, 1 meter long, right? And you have epsilon relative is equal to 2 rho. So rho is this measurement. It's the diameter, the radius. And you want the capacitance. So how do you do it? Anyone? Remember, it's a cylinder tube. How about it, Ben? I'll start with you. What do I do? I want the capacitance between the inner and outer surface, right there, per meter. What do I do? You're on mute, Ben.
Yeah, you assume Q like you did before.
All right, you're going to assume Q is uniformly distributed over the entire inner conductor. So you assume Q. Now, next step. Go ahead. Now it looks just like a line charge, basically, per meter. You got so much charge per meter, right? Now, what's the next step? You're right.
Find the D field.
Right, and you know from Gauss's law, this is cylindrically symmetric. So if I put a Gaussian surface around there, the integral of d dot ds is equal to the charge enclosed, right? If we're going per meter, the charge enclosed is Q, isn't it? Right? Everybody see that? Carlin, can you all see? Can you see what I'm doing here? I'm just making sure everybody can see it. Can you see? I mean, if you can, let me know in some way, shape, or form. Nod the head or give me a thumbs up. Something. You can you see it or not? I mean, the integral of d dot ds would be the charge enclosed. My surface d dot ds is going to be at a radial distance rho. It's just this surface right here. Can you all see it? All right, well, what is d dot ds? It's what? The perimeter of that circle of radius rho times the length, which is 1. So this breaks down to what? 2 pi rho d rho is equal to Q, or d rho is equal to Q over 2 pi rho a rho. How many see that? I got to make sure that I'm not just talking, sick of it. Are you all with me? Okay, now after that, what do I do? How about somebody else? How about Haran? Can you help me out? What do I do after I have the D field? I think you need to put your mic down or turn your mic on again.
Oh, sorry, I forgot that.
There you
go. And then we find the V from R1 to R2.
Well, we first do one thing. We find E, don't we?
Yeah.
How do you find E?
E is D over the, how to read that?
Epsilon relative.
Epsilon.
Times, and epsilon relative is 2 rho, right?
Yeah.
So that means my E field is Q over what? That would be 4 pi rho squared a rho, correct?
Yeah.
Now that looks just like the E field from a spherical charge system, if you look. Its varying is 1 over rho squared and has a 4 pi term downstairs. And I also have to multiply by epsilon naught, right?
Yeah.
All right, now the final form to get the voltage between A and B, or B and A, what do I do? Okay, minus the integral from A to B of this E field, Q over 4 pi rho squared A rho, and there's an epsilon naught in there, and I dot it with DL, which would be A rho dot D rho, and the A rows go away. And when I do the integration, I'm left with Q over 4 pi epsilon naught, and then there's 1 over A minus 1 over B. If you integrate 1 over rho squared, you get minus 1 over rho. Evaluated between A and B would be 1 over B minus 1 over A, but it's got a minus sign, so it's 1 over A minus 1 over B. That's VBA. Finally, how do you get the capacitance, Ron?
It's C is equal to
Q
times
over, no,
Q over V.
Yeah,
Yeah.
I'm only doing this interaction to make
And
sure that
it's
you get
4
this.
pi.
And that would be what? Simply 1 or 4 pi epsilon naught over 1
Epsilon.
over A minus 1 over B, right? That's exactly the formula for a spherical capacitor of constant epsilon. You all see this, class? Or of epsilon naught? All right, that's it. And instead of A and B, I have R1 and R2, but you can make the appropriate changes. Finally, the last thing I have, and unfortunately this one didn't render real well, I don't think. Well, I put in E field 10AX plus 10A plus 20AY plus 40AZ in the region 1 and assume rho S is 0. So fine in region 2. So here's what it came down to. You have two regions. One is this. The second is this. And they're separated by, see how this is supposed to be X right here, should have been going. What I'm trying to do this, but I don't think I'll be able to right here. What I'm really trying to do is show that region 1 is for X less than 0. Region 2 is for X greater than 0. Do you all follow me? So if the region is divided up by the value of X, it means the plane that is the interface between the two surfaces is the YZ plane. Can you imagine that? For X greater than a certain value, it's got one value of epsilon. For X less than a certain value, it's got a different value. So the YZ plane would be the dividing point, and this would be at X equals 0. Do you all see that? I can write it down. This is region 1 for X less than 0. And then down here, it didn't show up very well. This would be for X greater than 0. Forget the value of 0 itself. That means the YZ plane is the tangent plane. And when you look at this, you can see this is the tangent component of the E field right there, right? That I highlighted in gray? Can you see this right here? The 20 AY plus 40 AZ would be the actual tangent component, right? How many see that? It's hard to read your faces. Yeah, that means, and E tan 1 is equal to E tan 2. The tangent value of the electric field on one side of the boundary is the tangent on the other, period. So I can just say that E tan 2 would be equal to just 20 AY plus 40 AZ. Agreed? Everyone? All right, how do I get the normal component?
It's just 10AX.
Well, the normal would be 10AX of the E field, right? So E normal, right?
Of the
Right, E normal would be 10AX, correct? And that's in region 1. I better put 1. Well, now I need D normal 1, right? So D norm 1 is equal to what, Tyler?
It's E times the epsilon relative of region 1.
Now you come here, now you can see that region 1 has an epsilon relative of 3, right? Matter of fact, I might as well just call it epsilon relative 1.
Epsilon.
Epsilon relative region 1, pardon me. And then it's going to be times epsilon 0. Right, times E in region 1. And the E in region 1 is 10, right? All right. Now that has to be equal to D normal in region 2, correct, class? So what's D in region 2? Well, it would be epsilon relative 2 right, times epsilon naught. And then it would be times E normal, right, in region 2.
And those two are equal because rho s is 0, is that correct?
That's right. If rho s is 0, D1 is equal to D2. Since there's no rho s, and this is in region 2. Now, y'all see what's going to happen here. I'm really going to just, because of this equation, I'm going to divide this side by epsilon relative epsilon naught, epsilon relative 2 epsilon naught. And I'm left with the ratio of epsilon relative 1 over epsilon relative 2 times 10 is epsilon, or the E normal in region 2. And it's actually in terms of AX2. And I can therefore get what? I can say that D or E sub X2, this would be the X component, or just E normal, I guess, into would be equal to epsilon relative 1 over epsilon relative 2. So epsilon relative 1 is 3, epsilon relative 2 is 6. So it'd be 1/2, correct? And then it would be times 10 AX, or simply 5 AX. And I'm putting this in here so if somebody missed class, they can go back and look. Agreed? And that's how you do that problem. Okay. You've got, you can see this in real time, can't you, if you look on OneNote? There should be real-time changes appearing. All right, back to the lecture today. We're done with chapter 3 and we're starting chapter 4. Now, class, magnetostatics is similar to electrostatics, but there's one big twist that I'm going to get to. So this is chapter 4. And I'm going to actually open the book and talk about a few things. And if you want, I can put slides up. But I prefer to use the book. You have the book in front of you, right? Does everybody have the book? All right, if you have the book, if you turn to page 209, and I'm going to give you a brief introduction in my own words. Magnetism is something that we've known about since Egypt. I mean, they've known about lead acid batteries, or really chemical batteries and magnetism since Egypt's time. And they really, nothing much was done with it for about almost 3,000 years. They just noticed that it was kind of a neat phenomenon to look at, but nobody actually used magnetism for anything until about probably 1830, 1820 in there, when all of a sudden, actually a little bit before that, Ben Franklin was the guy that really took note of electricity and had electrical charges. And then Ampere and Farad and a lot of these guys, Weber, they all started taking a look at what you can do with it. So the first thing they noticed was with lodestones. and he talks about this right here, that they found that there's naturally magnetic materials in the earth. Lodestone's one of them. You can also see iron get magnetized, but iron has to be refined out usually. It doesn't occur, and I guess in a high enough concentration that you can actually magnetize a rock unless you refine the iron from it. I don't know that for an absolute fact, but I believe that's true. So with magnetism, you'll never have, well, you will, it's when you get to the, if you ever get it to take a course in really quantum physics and high energy quantum physics is something that they discuss, you'll find that in the macroscopic sense, there are no magnetic monopoles. You can't find a positive chunk of magnetic charge and a negative chunk. It's impossible. They're always in dipole formations. They always have a north and a south pole. You can think of the north pole like the plus, the south like the negative. It really doesn't matter what you call them. North and south were just something they use because the magnetic field of the earth emits from the north pole and basically it closes at the south pole, but that's the only reason we call it north and south. It can be plus and minus, however you want to think about it. The magnetic field lines here are like the electric field lines. They always come out and they close on the system. Now, what's not shown here is that they would be continuous. And the divergence of the H field is zero because the divergence of any vector quantity implies the charge or the something that created it. These things, there's no magnetic charge, so there's divergence of B is really zero. Now, that said, I got to ask you some things. How many know what cross products are? Y'all did them before, right? And the way I always talk about cross products, he gives some formulas here, is I like applying the right-hand rule. And it says this in a nutshell. If you have any two vectors, and I'm going to say if you have a vector A and a vector B, if you take your right hand, and I love the right hand rule, and take the index finger in your right hand, it presupposes you have a right hand. And to date, I have never had a person in my class without a right hand, so they can always use this rule. Take your right hand and take your index finger on your right hand, put it in the direction of the first vector. If I wanted, I'm doing this A cross B, and I'm going to call that C. And then through the small angle, not the large angle, you're going to go from A and you're going to use your index finger and just rotate it into B. So if you do that, A cross B would result in your thumb pointing in the direction of C. In this case, it would be pointing straight down. Just do it. A cross B. I'm trying to show A and B in the horizontal plane. And if you take A and cross them to B, your thumb points down. And that's C. That's the way a cross product works. Now, mathematically, we could go through the crossing operations in every coordinate system, but what does your instinct say? AX cross AY is what? Just do it. AX cross AY is anyone. A Z, right? Isn't it? Y'all remember doing this?
No.
You never did cross products, honestly? How many have? Just tell me, because you're supposed to have had this before in math. You didn't have this around, really? No,
I don't
Carlin?
remember.
You don't remember? Did you have a Carlin or Yiping? Did you guys have it? No? I'm not sure they're there. Anyway, trust me on this one. This is typical. So AX cross AY is AZ. And here's the way it's done generally. I'm going to show you a trick. Normally you put X, then Y, then Z, and put arrows this way. And then take one and go this way and put a plus sign. Now, what it means is if you have a first vector and a second vector, this will be the third vector. For instance, Y cross Z will be X, Z cross X will be Y, and X cross Y will be Z. So this is for positive. Now, then you do it backwards. You put Z, Y, and X, and you draw it this way, and negative. So if you have Z crossed Y, you get minus AX, Y crossed X, you get minus AZ, and X cross Z, you get minus AY. Did anybody see this before? Anybody? This is the standard way we always teach this stuff. This is going to be for the vectors. This is crossing where everything, I'm going from X to Y, Y to Z, and Z to X. The other way, I'm going backwards and they're always negative. So tell me what this is. What is AZ crossed AY? Anyone? Just look.
Minus AX.
Right. Something else about cross products. The vector it crosses into will not be in either of these two directions it came from. It's always orthogonal. So how about this one? What is AY crossed into AX?
Negative AZ.
Right, minus AZ. Good with that? And we can do it with cylindrical and spherical coordinates too. I don't know if he has it in the book here, but in spherical coordinates, like they're normally grouped R, right? And then it's what? R, theta, and phi, correct? All right, these are all positive. R, theta, phi, this way, all positive. If you have R, I'm sorry, if you have,
Professor, could you scoot the paper over?
yeah. I'm just showing you the crossings in spherical coordinates. The coordinates are R, theta, and phi. If I go R cross the theta, I get positive A phi. A theta crossed A phi, I get positive AR. And then A phi dot A crossed AR, I get positive A phi. If I go the opposite direction, they're negative. So I'll ask you one question with spherical and we'll break out of here. What is A phi crossed into AR?
A theta.
A phi crossed AR is A theta, right? Are you good with that? Everybody? You know, I don't know if Whitmer's book has this. It might somewhere, but this is something that the crossing operations, I can put them up there for you, but you always take, I mean, for cylindrical coordinates, what are the terms? It's rho what? Phi and then Z, right? So if you have rho crossed in a phi crossed in a Z, it's a right-hand system. Well, these will all be positive. And if you're going this way, they'll be negative for the crossing. You with me, guys? And I'm showing you the trick I've used since college. That's the way they taught this. And I don't get hung up with that. I use the right-hand rule if you have a problem. Okay. What can't you, oh, sorry. That better? Forget that. You good with this, class? All right. Now, if you just Google cross products or crossing vectors, unit vectors, it'll probably come up on Wikipedia and they'll show you everything, like even for arbitrary coordinate systems. Now, I flip the page. Are we supposed to get rain today, by the way? Anybody know? I haven't Googled the weather, but I'm asking for a reason.
I don't think.
No? This afternoon, I'd like to take my boat out. All right, so now, after that little discussion about cross products, yeah, if you have two vectors, you can also do this. Do you remember seeing this in math where they show you, if you take A cross B, you just write the unit vectors ax, ay, and az there, and then the components of the first vector, components of the second vector, and do the determinant of that. Do you remember doing that in your linear algebra courses? You can do it that way too. And these are for arbitrary vectors. Now we're going to get into something called the Biot-Savart law. You've had this in physics, but you probably don't remember it that well. It's this law right here. And I'm going to show you what it means and how it is. If you look at this just for a second, doesn't this have a lot of similarity to the differential electric field from a point charge? Remember, for a point charge, it was Q over 4 pi r squared, wasn't it? Or dq over 4 pi r squared for the differential electric or differential D field. Now, well, for this one, it's got a 4 pi r squared here, but here's the difference. You have IDL, which would be the current element causing the H field, crossed into a unit vector to the point where the H field wants to be observed. And it is the Biot-Savart law. So I'm going to show you what this means. This is on the bottom of page 214. When I have DH is equal to IDL crossed into a unit vector, and he calls it A21, I think, or A12, pardon me, A12, but I'll show you what this unit vector is all about, over 4 pi r squared. Here's what it means. If I have a differential amount of current right here, that would be IDL. Now note, this is a vector, a differential vector current. So it has a sense, it could be DZ would be the differential length, but it would have a vector sense, AZ. Y'all follow me on this? So it is a differential vector times I. Right there is the I. And I want to know what the differential H field is out here. Well, that would be equal to IDL crossed into A12. And here's how you get it. This is the vector R12 here. It's pointing from here to the point of observation of the H field. Can you all understand that this differential H field is just the H field at this point that we want to figure out? We don't know it. It's IDL crossed A12 over 4 pi, and then it's going to be R12 squared. Now the A12 is nothing more than R12 vector over magnitude of R12. It's a unit vector in the direction of the radius vector drawn from the source to the point of observation. And I'm going to do an example of this so everybody is with me. Y'all with me so far? Let's do it together. So if I have, say, 10 amps in the Z direction, all right, and it's differentially thick, it's DZ high, and I want the H field, that'll be at the origin, 2 meters away, and make this angle 45 degrees, and I want to know what the H field is out here, the differential H field. We're going to do this problem together, okay? Everybody with me? Now watch. If I have DZ, it's in the DZ direction, and there's a 45-degree angle to this radius vector. This is really the magnitude of R, right? You agree with me? And I'm going to say that this thing, for the benefit of the people, I'm going to call this the X, or this the Y x-axis, and this the Y-axis. And this 45-degree angle is going to be with respect to the vertical axis, but it's going to be in the YZ plane. So it's going to be at X equals 0, if you can imagine that. So my differential H field will be equal to I, which is 10, times the differential length DZ in the AZ direction. Do y'all follow me? It's divided by 4 pi, but now I need to get R. Well, the magnitude of R is 2, so R squared would be 4. Do you agree with that? Remember, I need R12, if you see it up here, R12 squared. If R, this is R12, is 2, squaring it would be 4. Agreed? Now I need to also get this unit vector, and here's the trick on this one. I said it was in the YZ plane, so this actual vector R vector, 1, 2 vector would be equal to 2, that's the magnitude, and then it would be times, you have to wait by a cosine and then a sine, a cosine of 45 degrees to get the Z component and the sine of 45 to get the Y component. They happen to be the cosine and sine is the same at 45. So it's 1 over the square root of 2 here times AY plus 1 over the square root of 2 AZ. Can you all follow me that that would be vector R, class? Give me a show of hands if you can. If I said it's in the YZ plane, this has to be vector R. Move this over. So if that's vector R, the next thing I need is unit vector, AR12, and that's R vector 1, 2 over magnitude of R, 1, 2. And you can see what happens here is you just get 1 over the square root of 2 times AY plus AZ. Everybody agree with that? I mean, can you guys see what I'm doing? Okay. Right. Just, okay. So now when I put in the unit vector, remember that's a crossing operation. That's going to be 1 over the square root of 2. I can put the square root of 2 down here. And it's going to be AY crossed into AZ, or plus AZ, pardon, plus AZ. Okay, so we're down to this point. I have 10 DZ AZ crossed into AY plus AZ, right? Over 16 pi. That means DH here will be equal to 10 over 16 pi times square root of 2 downstairs. And now, what is AZ crossed AY, class? I'm doing the crossing operation. AZ crossed AY is?
Negative AX.
Right. And what is AZ crossed AZ? It's 0. A vector crossed into itself is 0. Okay? So you don't have another term. In other words, DH is in the minus AX direction. Y'all with me? Now that's the differential, how to get the differential H field. If I went a step further, and I know I am out of time, but if I went a step further and I wanted the total H field, then in Wentworth's book, he says, well, find the differential H field and then integrate it over the entire length where the current exists. Does this make sense to everybody? You guys have time for me to actually do an example where this is applied to an integration class? All right, I want to do it. And I want to do, I mean, the classic one is the infinite line. And it probably does that one first. That's on page 216. And 217 does the loop. I like the loop one first on this, for this case. So let's do this together. Now work with me. And then we'll finish up. This is on page 217, but I want to do it from scratch. You can look in the book if you want to. So this is the classic loop problem. And try to draw yourself a loop like this. And the loop has a radius A, and it's concentric with the origin, or it's in the XY plane at Z equals 0, and this is the Z axis. And we're going to have a loop of, we're going to have a current going around here, I, in the radial direction. Can everybody imagine that? If you want a better picture of it, it's in the book right here. But it's just a loop, and I'm assuming I've got a current circulating this way. And now I want the value of the H field right there, the differential H field on the Z axis. So I pick my point here, and now I draw a vector down here. That is R1, 2. And I'll get to that in a second. And there's going to be a differential amount of current causing that. So this would be like my IDL would be equal to I Now notice something, this is important. This has a radius A, right? When I talk about the arc length right there, that's really the radial distance A times d phi, right? So the D, instead of the one I had before was dz, it would be times A d phi, because that's the length of a differential arc. Do you all follow me on this, guys? And it would be in the A phi direction, right? Can you all follow me? That I times, this is effectively dl magnitude, and that's the direction of dl. Now, when I get dh at this point on the z-axis at a height z, I'm going to call the height z. If I want the actual differential h field up here, then I can say dh is equal to I dl, so it's equal to I times A d phi, A phi, crossed into a unit vector over 4 pi r squared. I want you to look at R12 here. R12 would be equal to, in the radial direction, would be minus A rho. In the vertical direction, it would be plus Z A Z. Do you all agree with that? Hope you can see it. If I go from here to here, I go minus, I'm going towards the origin, right? Because rho is 0 at this point. So I go from here to here, it would be minus A rho. A is just the radius, correct, class? And then I go upward. I go from 0 to Z, so I get plus ZAZ. That's the radius, or the radial distance. Now, when I take a look at that and I square it, I would get A squared plus Z squared. That would be R squared. Do you agree with me? I'm putting that downstairs. And now I have to get AR12. So AR12 would be equal to R12 vector over the magnitude of R12. Or it would be what? Minus A rho plus Z A Z over this to the 1/2 power makes this to the 3/2 power. Do you all agree with that, class? Now remember, this is in his book, but I'm trying to do it in a way that, in a short logical operation. All right, now here's where it gets tricky. I'm going to say DH, the next one. I get all the constants out in front. So I get I right here, I get A, I get D phi out in front, and I get 4 pi. This is a constant. I've got A squared plus Z squared to the 3/2 power. And now I go through and do the crossings. Well, A phi crossed into A rho is what? Phi crossed rho would be A minus AZ, right? But with a minus sign in front of it is plus AZ. So it's really A, AZ. And then what is A phi crossed into AZ? Minus A rho, right? Remember how the coordinate, it's what? Rho, phi, and Z, right? And if I have A phi, sorry, if I have A phi crossed in AZ, sorry, I said it wrong. It's going to be positive A rho, pardon me. So this is going to be positive A rho with a Z in front of it. You all with me? Now I'm going to just say this one time. You see A rho here? A rho, a unit vector in the radial direction, is really going to be cosine of phi AX plus sine of phi AY. I have to do this because I can't do an integral of, when I have a d phi integration and I have A rho here, I cannot do that integration without first breaking down A rho into the X and Y coordinates. Because remember, when you say A rho, it's not at a unique angle, it's for all angles, isn't it, class? So you have to break it down like this. And now I'm just going to say this. If I do this and I replace A rho with this, I want you to notice when we find the total H field, we're going to integrate this from 0 to 2 pi, right? This would be integrated from 0 to 2 pi. Do you agree with me? All right, now watch. What happens when I replace this A rho with this? What happens when you integrate a cosine function over a period from 0 to 2 pi? What do you get? Remember this. This is important. If you take a cosine, you integrate from 0 to 2 pi, what do you get? 0, don't you? The area above is the same as below the curve if you graphed it, right? The integral of any sine or cosine over a period is 0. That's one of the beauties about this. So when we integrate the cosine phi d phi from 0 to 2 pi, it goes away, it becomes 0. And sine phi from 0 to 2 pi, it becomes 0. You all follow me, guys? So these terms will go away, and I only am left with AZ, and that's sort of the gist of it. Now just watch this, so you can forget about that, and follow me on this last part, all right? When we integrate this d phi, you'll notice that there's nothing that's a function of phi in there, right? Can you all see that? Only d phi. I is not a function of phi, A or Z. So when we integrate d phi, we just get phi evaluated from 0 to 2 pi or 2 pi. And that makes our H field right here equal to I and then A squared. A squared is the radius, right? AZ over 4 pi A squared plus Z squared to the 3/2 power. And that is the H field on the Z axis right here. You're going to get this, and this is on Z axis. That's shown in his book on page, it's on page 218, formula 4.9. He has it right here. I have 2 comments before we move on this, and I want you to hear me. You all see that equation, right? That's anywhere on the Z-axis. Now you'll notice that I assumed the direction of the current was looking down the Z-axis clockwise, right? If the current was going in the other direction, the H field would have a minus sign. The H field would reverse polarity. Can everybody understand that? So the direction of the H field has a big deal to do with the direction of the H field. I mean, the direction of the current I has a big deal to do with the direction of the H field. The second thing you have to notice is this. Where's the value going to be a maximum? What is it? Take a look at the equation right here. Versus Z, where is this the maximum? Anyone?
0?
Yep. It's at Z equals 0. What is the value going to be? Well, set Z equal to 0, and what do you get? You get IA squared over 4 pi A cubed, and it's really going to be H at Z equals 0 is equal to I over, actually this is not 4 pi. We integrate and we got a 2 pi up front. This is a 2, my bad. It's going to be I over 2A. And that would be amps per meter. That's at Z equals 0, and that's the maximum. Okay. H field have to do with magnets. I'm going to have to break it off here. I went about 15 minutes over, but I needed to get that out of the way. Now for homework, I'm going to tell you what I'd like you to do for Monday. I was going to give you a quiz Monday, but I think we'll postpone it till Wednesday so we get a better feel for this topical material. What I'd like to do is this. I want you to read through this section right here. Take a look at the example of the infinite line right here. He has an infinite line of current, and he's going to get the H field from that. You're going to see it's very similar in form to the actual E field from an infinite line of charge. It varies as 1 over 2 pi rho. And it's weighted by the current I, but it's in the phi direction, not in the radial direction. I want you to read through these 2 examples, and then the section on the solenoid, just the solenoid section for Monday. Y'all know what a solenoid is? Just a lot of wire wound around a tube. It's called a solenoid. And if it was, the tube was bent around an axis to make it like a circular thing, then it would be called a toroid. And you've heard these terms, I'm sure. So I want you to read those, and I'll give you some homework problems. And right now, I'll answer any questions you have. If you want to ask any questions, I'm going to stop about homework or anything like that. Anybody got anything for me? Nothing?